Okay, so now let's see how, if we can come up with an approach to see how the uh, different factors, such as alignment of fillers, affect electrical conductivity. We're going to describe it in two ways. First, we're going to look at percolation threshold. And so the experiment they did, it was a simulation based on this paper. It's not an experiment, it's a simulation. And so what they did was they randomly placed particles of the same size inside the matrix. And they at every time, as a function of the number of these particles, they investigated if there was a percolated network between the two ends have formed or not. They chose a parameter theta of mu, which is the angle between the particles and which is the angle between it's the maximum angle between the fibers and a straight line, or rods and a straight line. And so they did this experiment for many, many different cases. And in each case, for each value of theta mu, they randomly placed n number of particles inside this box. And so theta mu, so basically the location of each particle is chosen randomly. The orientation of each particle is also chosen randomly, such that it's between 0 and theta mu. Basically plus minus theta mu, between plus and minus theta mu. So for instance, theta mu equal to 90 degrees is perfectly random because any orientation is possible. 0 means all the fibers are in this direction. And so they changed this number, 420 or 450, 500, 600, 690, is the number of the sticks. So in some sense, you can think of it as volume fraction, because the more of them, the higher the volume fraction of these particles. Two trends are very, very interesting. First of all, we cannot talk about the percolation itself. We have to talk about the probability of percolation, because these rods are randomly oriented, distributed. Number one, as you increase the number of particles, percolation, the probability of percolation moves to the left, which the angle at which this probability percolation jumps up moves to the left, which means it's more likely for them to percolate. A percolated network means probability of percolated network 1, and 0 percolation is here. So for instance, if you choose the cutting angle to be very low, about 10 degrees or 15 degrees, it's very difficult to have a percolated network. So basically, if all your particles are like that, it's very difficult to have some percolation. And you can easily imagine that, because you need some particles to go like that to bridge these other particles. So the higher this theta mu, means the more randomly they're oriented, the higher the probability of reaching a percolated network. In addition, the higher the volume fraction, the higher the probability of reaching the percolated network. However, so basically, one trend, if I have higher volume fractions and more randomness, percolation threshold will happen earlier at the lower volume fraction. But that does not mean that if I increase the alignment, my conductivity will always go down. That doesn't mean that, and I'll tell you why in the next slide here. So this is an equivalent of the experiment of the previous slide. This is equivalent of the theta. And so basically, this is 2 theta, so theta is half of that. So basically, what they said is that if I increase randomness to my data, my conductivity goes up. Okay, and that trend makes sense because a percolation threshold happened. However, what is a little bit counterintuitive is that the maximum happens here, and after that, conductivity drops. Basically, if you, this way, going from here to here means you're randomizing the alignment. Up to here, it increases it. After this here, it drops it. And the reason of that, and here you can see another case happens with different volume fractions. And the reason for that is, if I have these particles, okay, that now electricity can go from this end to this end. But if I can make these two still more aligned, okay, now the whole length from here to here has been reduced. Okay, so if I have enough randomness that, as a result of which, that percolated network has formed, slightly reducing the randomness will probably help me, because I align some of the particles with the direction that I want electrical conductivity to happen. So I am going to stop here, and we are. Oh, actually, I can continue on this one because we still have time. So now the question that you guys may ask is, how would I align, for instance, carbon nanotubes in my composite? Well, there are different ways to do that. One way that I'm explaining to you here in this slide is to use electrical electric field. So imagine I have a carbon nanotube here, and I apply a voltage between these two ends. And so there's an electric field like that. This electric field will induce charges in my carbon nanotube like that. And these charges will be pulled by the electrostatic field. And so that tends to align the carbon nanotube with the electric field. Note that even if I apply electric field in the opposite direction, the effect will be the same, because in that case, I will have a negative charge here and a positive charge here. I'm showing it with yellow. This guy will still apply a load this way, and this guy will still apply a load this way. And so the guy will be aligned. However, if there's any slight variations in the electric field, spatial variations, this guy may migrate from one end to the other. Okay, so that's why if you want to align carbon nanotubes with this way, what you typically end up doing is basically not applying a DC electric field between them, apply an AC electric field. That because with both orientations of electric field, with both orientations of the electric field, the carbon nanotube gets aligned. So if I want to fight electromigration, I would use AC signal, and I use typically high frequency. And so, for instance, this could be the case where you have an epoxy that you add carbon nanotubes to it, and you apply an AC field, you align it. So imagine carbon nanotubes are here with epoxy, and voltage is applied between here and the edge of the cylinder. And you can indeed get carbon nanotubes aligned. The carbon nanotubes, if I look from top, if this is the center of the cylinder, carbon nanotubes will be aligned with like this, because that's the electric field. Typically, you need very high voltages because you need high electric fields, because you're supposed to fight the Brownian motion, and you apply high frequencies. But this method is often good when you're close to or below percolation threshold, because if you pass percolation threshold, this high voltage means you pass a current through your sample and you burn it. So after you align the carbon nanotubes, now you have to cure the whole sample. So I'm going to stop here, and we are going to start the thermal conductivity.